searching.
Oh, our guest has arrived.
Well, we're searching. We're so happy that
Wow.
OpenNerve is here. Yay!
Yay!
Good to join you guys. I think I had an
Okay.
old Google Meet link. I was waiting in the
Yeah,
waiting
it's
in the
okay.
lobby there
It
for a while.
happens.
Whatever. You can.
Yeah.
Not sure how that got onto my calendar, but glad to be here. And yeah, glad to talk a little bit about the project I'm doing. So, I guess anything I need to know before getting started.
Just go
Just
for
know
it.
that you're awesome.
Yeah, you're great.
I mean, you gotta wait till the end of the presentation to judge that. All right, let me share my screen. All right, this might be tough. I'm getting the browser can't access your screen error when I try to share screen.
Oh.
Ooh, that's
So,
fun.
Maybe Firefox and whatever this StreamYard is don't work well together.
There's a chance that you need to enable permissions to share screen, which would be through your settings. And everyone loves to get tech support over a live stream, right?
I'll figure
It's
it
okay.
out.
Nobody's watching. Don't worry about it.
How many people are
There's
online right
definitely
now?
not people currently watching.
Nobody's paying attention.
It's
been
just
able to
us. It's
just
just
us.
you and Lee and me, and we're just chilling, enjoying the process of hanging out, enjoying the vibes. Why can't I find this post?
Yeah, how is everybody doing online? How have been the open source project so far?
It's been really great. I feel like we've had like a huge range of different kinds of projects and a huge range of different kinds of people. And yeah, it's been 5 amazing hours.
Well, thank you guys so much for doing all this.
My life? Maybe.
Yeah, we're happy to. I mean, it's great. We get to eat snacks, talk about hardware, and receive faxes. So I really
Nice.
What more could you ask for in life?
literally can't imagine a better afternoon and morning and evening
And night.
and night.
Jay says, we're real humans heavily invested in your tech support struggles. And that's so true.
Yeah, everyone's here for you, or nobody's watching, whichever one helps.
All right. I wish I could share screen to show what I'm going through right now. That would be useful.
You could,
If we could all watch you try and figure out how to
Yeah.
share screen while sharing screen, it would be quite beautiful. Sometimes you can export as a PDF and share that.
oh yeah, if you
Or you
Email
can send
us
it.
a
Yeah, you
PDF.
could, if you send us a link, we can
share.
we
if
can
you
share
give-
I
screen
think-
for you.
I think that might actually be the best option.
Yeah.
Okay.
Hit
Let
us
me
with the link in the private
email.
chat, and we'll make it happen.
All right. Private chat. Perfect. Can do that at least.
That's right. There's a private chat that y'all viewers don't even get
There's
to know
so much
about.
stuff going on there. You guys don't even know. It's all
Oh.
actually the good stuff.
It's so exciting in there.
Yeah.
All right. I don't think I can drop PDFs into the private chat.
No, you'll
No,
have
but
to
you can-
email
yeah,
us.
I'll email it to
If
you.
it's PDFs, feel free to email. If it's a link, you can drop it in the private chat. Whatever
So
makes
I just sent you the PDF.
Okay.
Also, guys, I swear I had like degrees and stuff in technology. I'm not usually this useless around computers, but
I don't know how computers work.
I've
so-
never. We didn't. Why did we teach rocks to think?
Yeah, we should never.
Anyone know?
I love it. I'm reading, I'm starting to slowly get into sci-fi because in my job, everybody's into, or not sci-fi, like fantasy, like Brandon Sanderson type stuff, because in my field, everybody's into it and keeps saying I should read it. And it's like,
What hasn't that man written?
it's almost frustrating because it's like I deal with hard magic systems every day. That's my job. I don't really want to read about stuff. where there's
You don't want to do it
rules to the
recreationally.
magic. That's all that electrical engineering is. Yeah, I guess I emailed that. So while it's trickling through the system,
Yes.
to give an overview. So I work actually at the University of Southern California. I am on a project called, we've sort of renamed a couple times, but right now we're going with OpenNerve because it's the sort of the simplest and most direct that we can find. And our mission is to develop an open source system for implantable autonomic neuromodulation. So that's a device that actually goes inside the human body that is connected to different organs, different nerves that like are outside of the brain that go to the different organs. And the idea is that we could hopefully allow doctors and allow researchers to record and then apply electrical stimulation in order to fix different diseases. So some examples might, ooh, there it is. So some examples might be for people who have like stomach problems, GI problems, who don't have good motility. This could potentially like be almost like a pacemaker for the stomach or for the colon. If you guys were online and you saw Cosmic's presentation earlier in the day, Cosmic is actually sort of our sister project. I would say they're a little bit farther along than us, but they were funded under the NIH under the same grant, and we work closely with them. And it's always fun to have people that are both like rivals and best friends, because I feel like it keeps you on your toes, but also because it's such a collaborative nature of like science as well as of open source, we can kind of share learnings and work well together. So if any of you guys are reaching out to Chris after his presentation, tell him I say hi. All right, jumping into the slides. So like I mentioned, we're funded through the NIH. So thanks NIH. I hope you continue to exist in the future. Big fan of them. The problem that they were trying to solve is something that I know personally as somebody who's developed different therapies in the past, and that many, many other researchers I've talked to have, which is in order to actually take a scientific discovery and move it to the clinic, there's basically, you need a device that is very sort of safe and well tested, and that can be trusted to be put in somebody's body without hurting them, of course. But the process to go through that, usually when a company takes a device through that process, the company wants to keep everything they do a secret. They want to lock down all the regulatory testing that's done, all of the sort of the results of the testing. So like the actual data that shows the device is safe, that is very valuable proprietary data. They want to lock down, of course, the design of the device, the mechanical, how to build it, the electronic schematic. And so if a researcher has a brilliant new idea, they'll have to just either beg a large company to work with them, which comes with all sorts of restrictions, and usually the researcher can't modify anything, let's say software, in order to like try something new, or they'll have to develop a device themselves, which, let's be honest, funding is tough. Like these devices can cost millions and millions of dollars to make and to test and to prove that they're safe. So the NIH wanted to create a sort of a third option, an open source system where they would sponsor the development and then the early testing, and then anybody could access it and use it to sort of either use as is to test a new therapy if what we're building already works for it, or to make modifications easily because it's open source, and then have a maybe not a super easy regulatory path, but at least a shorter path. So anyway, that's the goal. Next slide. So in response to that, my boss, Dr. Ellis Meng here at USC, wrote a grant and got funding to develop this OpenNerve platform. So OpenNerve is, the idea is it kind of looks like a traditional implant, like a pacemaker, but it has a lot of new and interesting, both like new capabilities, as well as it being open and flexible enough to try many different things. So the core of it is this implantable pulse generator, this IPG, which we'll talk more about later. There's also a number of different like leads or sort of cables with electrodes or with sensors on them that plug into the IPG. And then the IPG has Bluetooth as well as inductive like wireless charging. So it can be charged in the body and it can communicate with devices outside the body. All of this is being released under the Creative Commons CC BY 4.0 license. And don't worry, I'll show many, many times the link to our GitHub so you guys can go check that out. Next slide. So like any sort of collaboration, or basically any sort of large government grant, there's many different people involved that are all doing various different components of the system. I just want to highlight this. This isn't just our group. There's actually two private companies involved that have thankfully agreed to open source what they're doing. MedAlly, which is a contract manufacturer, they're developing a number of the leads, which I'll show in the next slide. Stay on this slide for now. As well as, no, stay on this slide. No. Yes, sorry. Thank you for bearing with me. Anyway, MedAlly is designing, leads, and then the case, sort of the hermetically sealed enclosure for the IPG, which you might think, oh, you just slap a case around it, but it's actually it takes a lot of really good precision machining and a lot of sort of careful design to make something that is made out of materials that are safe in the human body, such as titanium, can actually charge something wirelessly through this metal enclosure. and most importantly is sealed in an incredibly robust way, right? These things need to stay in people's bodies for hopefully their entire life working properly. And so there has to be basically a 0% chance of any water getting in and causing failure. There's also 3 groups at USC. Ellis Meng, who's leading the project, her group is also developing a tiny little, basically saran wrap style nerve cuff. Think of it as like that very thin saran wrap type material, but also with little metal on it that can go on teeny tiny nerves that are all throughout the body. So very precise targeting. And then there's 2 other professors, Hongbo Zhao, who's developing some mechanical sensors such as strain sensor, and Maral Musabe, who is developing some chemical sensors, pH, and then to detect different neurotransmitters, all of which plug into that IPG. Yes, next slide. Thank you. Like I mentioned, our IPG is kind of the, no pun intended, the heart of the system. And this is what it looks like. It has all the electronics inside of it, as well as a battery. It has multiple channels in it for stimulating, so applying electricity to the body, as well as for recording from the body. And it also has one of those ports up at the top is also I2C. So for you electrical engineers out there, that means that we can actually have digital devices on the ends of these lead cables that plug directly into our OpenNerve. Theoretically, we could chain multiple of our IPGs together. We haven't done too much of it yet, but like, for example, we have for the capacitive strain sensor, we're going to put a digitizer, basically a capacitance sensor, on the end where the sensor is, where the actually sensing element is. And then we don't need to worry about parasitic capacitance in the cable leading back to that OpenNerve IPG. But this is something I'm excited about because I think there's all sorts of things you could do with an in-body communication network. And again, for anybody who's involved in medical devices, you'll appreciate this. We actually, instead of powering the I2C lines over DC, it's actually powered with AC pulses. So there's square pulses that I can't remember the duty cycle, but basically we prevent any sort of DC charge happening in a cable in the body for just additional safety. In case the worst happens and that cable breaks, it won't, you won't hurt anybody by having a broken cable in the body. It'll be non-functional, but we meet those high safety standards that are required by the FDA. All right, so next slide. Next slide, these are just to highlight some more of the leads that MedAlly is doing. So these leads kind of they mimic things that are, well, except for the accelerometer sensor, they mimic things that already exist in the world. So for people familiar with a nerve cuff, doctors who use nerve cuffs already, or for doctors who use linear arrays, linear electrodes, we have versions of those that plug into our IPG. And I'll show a couple little examples here. I don't know if you'll be able to see them, but this is one of our nerve cuffs. You can see this is one of the larger ones actually. And there's 2 little platinum electrodes on the inside. And then you wrap this around a nerve in the body and close it using these sutures. And then over here, this is actually for measuring EMG. So measuring the electrical signal given off by muscles when they contract. And so the idea is there's a suture at the end. Look, it's a small suture, it just looks big on camera. And so you push this through the muscle, and then this little trumpet anchor here sort of hits the muscle on the other side. And then this metal part here, that's the part that actually picks up the electrical signals, and that's securely embedded in the muscle, and you can secure the suture on the other end. All right, next slide. So I'll go into some more details of all of this in a second, but before I do, I want to just talk a little bit more about, I guess, the motivation. So why does what we're doing matter? Why can't the traditional method of a company developing one of these medical devices, where are the gaps and where are the ways that it's failing? So in any product, whether it's consumer electronics or aerospace defense, or in our case, medical devices, between when sort of a scientific discovery happens and when that is turned into something that people can use, that is commercialized, there's this valley of death that's always talked about. For medical devices, that valley of death is basically the cost and the time necessary to create a device that will pass all of these regulatory standards that can be proven to be safe, which is of course the most important thing, and then the cost and the time to actually do the clinical trials, right? I'll be honest, the part that we're trying to fix or trying to improve, the actual design of the device, is not the most expensive part of that valley of death. That would be the pivotal trial, which can cost up to $50 million for a class 3 PMA implant. But there are a number of groups that don't even get to that stage. like I read a recent paper that tried to figure out all the money behind this, and I think they said that like, yes, the pivotal trial is the most expensive single component, but there's also, because so many groups fail at that initial like just developing a device that works stage, you could say the effective cost of that is like, you know, it's much higher than what it is on paper, right? So I guess the bottom line is many groups who have promising ways that they think will actually, you know, help people, especially help people who have diseases that are not like a large disease population. For example, people who are paralyzed, where they have this very high need to make their lives better, but there's not, you know, luckily there's not a lot of people who are paralyzed, but also that makes it harder for a company to justify spending the money to create a new device just for that patient population. This, you know, this limits the amount of therapies that can be translated, and by hopefully us developing a sort of an open source device and also developing a platform being able to disseminate this to anybody who needs it, we hope to sort of fix that and get, I guess, get groups to that first in human stage faster. All right, next slide. Yeah, this is, can probably skip this one. I think I said everything here in the previous slide. And yeah, just to highlight again what the sort of what's done currently. So when currently researchers, they have a couple of options, right? They can either use a commercial system off-label, which there are companies like Medtronic, Boston Scientific, Abbott. Those are sort of the big three in our field. They make very high quality devices that are used in millions of patients worldwide. Unfortunately, those companies are hard to work with. I'll just straight up say it. Like, I understand why. I've talked to many people in those companies, and it's expensive and time consuming for them to support research studies. But that also means that it's difficult, and sort of there's barriers to entry in terms of knowing the right person to even ask, in terms of, you know, doing something like doing research that the company might then pick up in the future. So it has to work out with the company's business plan. As well as with IP negotiation. Many times, you know, companies have their IP, universities have their IP. I've heard many stories where like the engineers and the executives at a company are all for this, the researchers are all for this, but then there's just sort of conflicts at the legal level that can prevent things from moving forward. So the other path, of course, is to build your own device, which just academic research labs don't have the resources to build almost never have the resources to build a device that can go inside a human being. The times I've seen it done successfully, it's been in collaboration with one of those larger companies. So there really is sort of a gap in the market, if you want to think of it that way, for a system that's flexible enough to be used for research, but also robust enough to be used for clinical research. All right, next slide. So yeah, there's background. I'll get into some of the like studies we're doing and kind of what stage we're at now. Just to be clear, we're not in humans yet, right? This project is very much ongoing, and while we have built a thing and we're testing that thing, as you can see, with many different partners for different diseases in like different animal models, we're still trying to figure out our path to that first in human. So we're hopefully one of these different studies that I'm highlighting here with one of our partners, those will be promising enough that they'll, you know, go forward and make a therapy and help lots of people. But this is still a work in progress. I don't want to oversell what we're doing. However, I am very proud that the technology that we're working on is being used, not just by us internally, but by people at different universities and at different companies, different startup companies, in order to try to actually develop new therapies. And I'll just highlight some in the next slides here. So this is a study. I won't go too deep into this. We're doing some studies that just kind of validate, make sure that our leads are safe in animals. So for example, we did a study with some of the more, you know, our IPG and then some of those standard leads I showed, where we basically tested if we could modulate the gastrointestinal motility of some pigs. The study went, I would say it went okay. We showed that our devices, or at least the leads, are safe. But we're actually going to do a follow-on study to look more into like, can the sort of the procedures we develop be used for an actual therapy? So stay tuned for that. That'll be in January 2026. Another study we're doing, and that we actually, if you want to, you can go and like look up and see the data that we've all released as open source, is for those very thin cuffs I mentioned earlier. So those cuffs, we did a study recently where we put those on rat sciatic nerves, and we tested both stimulating the sciatic nerve as well as recording it. to make sure that the cuffs could apply electricity safely without them breaking or without damaging the nerve. So I won't go too into detail about this, but if you want, you can look on the Spark portal, the Spark portal is sort of the same NIH program put together an open source database of a bunch of like basically really robust animal and clinical data, so that any researcher can go on and download the raw data as well as the analysis, all the code that was being used. And yeah, it's a very small data set we have up there, just 2 animals, but we have it up there as well as the protocol that we use to do the research. So feel free to go to those, go to those links and check it out if you'd like. And I guess it should be worth saying that as those studies I mentioned earlier move forward, all of that data will be released on the Spark portal in the same way, right? Like it might be a bigger discussion of what does open source mean for medical devices, but what we're trying to do is be as open as possible, meaning not just source files, but also the documentation around those files, the testing protocols, the fabrication protocols, and in this case, the raw data as well as the analyzed data from the animal tests we do. So hopefully that'll help somebody out in the field, especially if they want to like use our devices in the future or if they're interested in replicating the study. Moving on, we're doing some studies right now of some of the other sensors. For example, we're putting some of the electrochemical sensors on a rat brain and actually measuring the changes in neurotransmitter levels in a rat brain. Go to the next one. We're also doing several studies of our strain sensor, right? We have to validate this would work. The strain sensor is actually gone through a decent amount of development, and there have been some really interesting kind of discoveries made along the way, more on the engineering side of like, how can we make something that's both stable in the body, but also has a very high sensitivity. So if you go to the next slide, I think I highlight one of the new papers that came out of that group. Yeah, you can see there, if you just search for that name on Google Scholar, you'll find one of the papers that came out. They actually did they invented a brand new fabrication method where they stretched the sensor and then they coated it with this biocompatible like plastic. And then when they let it relax, the plastic wrinkled up, but I won't go too much in detail, but basically it prevented the sensor from expanding in the, I guess, what is it, perpendicular to the axis of strain, while allowing it to still stretch parallel to the axis of strain, which doubled the gauge factor. So just not by accident, but like as an unexpected benefit of this project, they figured out how to make stretch sensors that were twice as sensitive as before. And currently that group, as you can see there, is testing that stretch sensor on pig bladders on the benchtop. And we actually, here in just a little bit, maybe a month or so, we're going to start doing that chronically in an actual animal. So that'll be really exciting. And then I can't go into detail on all the different studies because some of them, if we're collaborating with the startup, they want to wait until they finish the study before announcing it. Though they have all agreed to release the data as open source, which we're very happy about. But here's just a couple that we can talk about. So one study we're doing is for like helping people who are paralyzed with bladder control. Turns out that there's a lot of problems that can happen with bladder and bowel movement after paralysis. And so we're trying to do several things to help that out with stimulating different nerves and being able to kind of bridge the gap over their spinal cord injuries so that they can more naturally both know when they need to urinate and then activate that. One of the just very small part of that project is to create a new sensor for measuring how full the bladder is. We are using the strain sensor, or we're testing that. We're also using electrodes and actually measuring the electrical signal that goes through the bladder. And you can think of that as, basically being more or less conductive depending on how much fluid is in there or not. So we're doing that in rats right now, and that looks very promising. We're also doing a study where we're using different electrical signals in order to block signals through nerves. So instead of just applying electricity that sort of activates a nerve, we also want to prevent signals from going in one direction. This can be very useful, for example, for patients that have chronic pain, because theoretically we could block those pain signals. And potentially, we haven't gotten into this yet, but one idea is that we could block pain signals from going in one direction while also stimulating and having that stimulation go the other direction. So to do both therapeutic stimulation and block at the same time. Should be very exciting. All right. I think for time, let's just skip all of these IPG development updates. This kind of gets into the weeds on some of the updates that we've been doing. we're releasing a new version of our IPG soon. We just finished manufacturing the PCBs for that. Oh yes, let's pause here. So development boards, I have one here. One of the things that we realized going through this project is that it's a very high bar to use like the actual implant device, right? Even for animal studies, you have to have obviously like the facilities and the veterinary staff, and to be able to do these studies safely and to be able to do these studies in a way that's humane. But you also just like need a lot of technical knowledge, and it's also expensive to manufacture the devices themselves, even though they're open source. So one thing we're doing is we're taking the PCB that's inside of those IPGs, and we're doing our best to give this to our collaborators as a development board so that people can, I mean, theoretically swap components, but also just like reflash and reprogram the firmware easily, plug in whatever leads, whatever electrodes they want. It can be powered by USB, but it also has a Bluetooth antenna on board, so it can be communicated with from, remotely. So yeah, so proud of this, and we're just finishing a batch of PCBs. I believe all of the PCBs are, I don't know, we might have one or two that are left over after the people that have already, sort of, we've committed to giving them dev boards. But just for anybody listening, if this is a project you're interested in and you think that having one of these development boards could be really like useful for you, if you're in the, if you're in this field and you want to work on it, please reach out and let me know. I'll set up a call, we can figure it out. And if there are any boards available, we can hopefully get you one to test with. So talking about our resources, I told you I'd add a bunch of links for our GitHub. Here it is. I just want to highlight that we are releasing all of the source files and all of the surrounding documentation on GitHub sort of as they're developed. Right now, we have all of the Gen 1.0 schematics and layout and the CAD, as well as our very early Windows control software and a lot of the test protocols for our IPG up. I will say we don't have the test results for those protocols because those tests are still ongoing. We will hopefully release those by the end of the year, no promises. But yeah, we are doing those tests, and as soon as the test results are done, we'll release those as well. For our standard leads, we also have like design diagrams, CAD models, and similarly benchtop testing plan. We also have the PCB files for those motion sensor leads that I think I probably went through way too fast earlier, but you can check them out on our GitHub if you want. The different groups, we have individual repositories for these other different labs that are creating sensors that plug into our IPG. You can just briefly see here what sort of files are up. Yeah, I encourage you to go in there, check them out. Also, of course, if there's a file or if there's a piece of data that would be useful that you don't see, just directly reach out to me. I'll put the very last slide, I'll have my email as well as a QR code. So yeah, feel free to reach out to me. I can probably find that, or I can just annoy whoever is in charge of development to like do an extra test or create an extra file that we can release. So we do want this to be as replicatable as possible. Go to the next slide. I also want to highlight that we're releasing this under the CC BY 4.0 license. Basically, all you have to do is give attribution. So cite us, say if you use something from our project, just say this is from the OpenNerve project. I know we set up our GitHub repository so you can cite the repository directly. We'll be releasing a few publications soon that just go over the specs of our device, so you can cite that as well. But an important thing is we're not restricting this to be sort of share-alike. So if you're thinking about starting a startup company, or if you have a company and you want to use some of our resources, you are allowed to use this. There's no need to keep things open source or to share any IP. We're happy to work with you, and of course, we'd love to support you in whatever way works best. But yeah, don't let the fact that it's open source stop you from developing IP around it either. One thing we want people to do is to be able to take, say, their patented lead or their proprietary algorithm, and be able to run it on our open platform. We don't want to restrict that. And then I think this is the final slide. Just showing that there's all sorts of different ways to work with us. Talk to me if you want to get a development board, or if you're interested in collaborating on animal studies, or us supporting you on any of that preclinical work. But also, like I said, we're working with a contract manufacturer that does have clinical experience. They are certified to make devices for human studies. So if you think that this platform could work well for you, we can put you in touch with them, and I can help with that relationship. Basically, get you whatever devices you need. I think I just go into some stuff that I already talked about, hopefully we can reduce cost and get people to take their scientific research forward easier. I think that we can probably just skip to the end and just go all the way to the acknowledgement slide. I want to at least say thank you to everybody that's been involved, because there have been a lot of people, right? Eric and Brooks at the NIH, they're program directors who sort of came up with the idea for this open source system. So very thankful to them. Our external advisory committee, these are people we met with a couple times a year who are sort of leaders in the field. This is Peng Kong, Tracy Kui, Jeannie Park, and Martin Schutler, and they've given us some really great advice of what's actually, of making sure we develop something that's actually useful. And then of course, everybody that's been involved in development or has contributed to the project so far, really, really thankful to all of them. So I'll leave it on this last slide. Just reach out to this cars@usc.edu. If you're confused by that, our center was originally the Center for Autonomic Recording and Stimulation Systems, and we're rebranded to OpenNerve, but we still have the old email. So you can reach out there. I'll also put my email in the chat if I can figure that out. I don't know why it's asking me to connect to YouTube in order to put something in the chat, but I'll put my private email in the private chat, and then maybe the organizers can share it. But I'd love to talk to anybody and everybody who might be interested. And yeah, thanks for listening. And thanks, Oshawa, for being good supporters of this project as well. I know that actually connecting with them has been really, really important for us. I'm not an open source person. I wasn't, like, before starting this project, I'd never interacted with an open source project at all, besides building things with Arduinos, but I didn't interact with the open source part of that. So you guys at Oshawa have been really helpful to just help me understand what open source means and how our medical project can fit in with that world. So huge thanks to y'all.
Thanks so much.
Huge thanks to y'all for being such a big part of the OpenNerve crew. Has been a huge part of the open source healthware movement and the work we've been doing there. It's been really great to get to work with y'all so much and really get to experience what it looks like to take something. Class 3 medical devices are not often open source, so getting to be able to see that is pretty damn cool.
Like, just a really good job just now highlighting some of like the challenges and things that you guys are working through. I think it's really important because I think a lot of people don't really understand the difference and the nuance of certifying and like working with medical devices. So it's really great.
And then we've got a question from Jern D, who's wondering, you probably went over this, just wondering what CAD tools you're using for this.
So this is I'd say a bit of a point of contention, actually. So one of the I guess great things about working with a private companies that already have engineering staff is that they already have a pipeline to build things, but they often don't use open source tools themselves. So like our current generation, all of the mechanical CAD is done in SolidWorks, and all of the ECAD is done in Altium. I will say one of the things I'm pioneering here at USC, one of the things I'm pushing for at USC is to move all the electronics over to KiCad so that it can be used for free by anybody. That should be done, I would say, before Christmas, and we hope to release CAD in an open source program, at least for both the rigid, like the dev board PCB, as well as for our implant PCB. Maybe this is a question for the community. What mechanical CAD program is best for open source? Because I know FreeCAD exists. I know there's something from Google. What do you guys recommend?
That's what do the people recommend these days? Because there's a lot of options, and I don't make things like this.
Well, I think it's a good question to put to the chat, and then hopefully some folks will be able to chime in with some answers and give you a few suggestions.
Yeah. And then just to be a bit of a guy who has a job and loves it, I will also note that OpenNerve is also one of the groups that we did a highlight on. So you can see that on our website and also get to read a little bit about it, and all the links that you could possibly need to get a hold of them are all in there. And surprisingly, it was Alex that was interviewed for this, so you can read his words as he talks about his project.
And also at the Healthware conference as well. There, all of the recordings from Alex's talk about OpenNerve are available on our YouTube as well. So if you want to hear more.
And Jordy also chimed in and says they're quite biased because they helped to build 123D, but FreeCAD is the most accessible probably. And I would believe it.
Well, thanks, Jen. I'm the electrical engineer by training. So I've actually never, I think in college, I made the worst ever airplane model in like SolidWorks, and that's the extent of my CAD knowledge. But I'll tell the people working in CAD to try to switch it over to FreeCAD. I got to run, but thanks you guys, and best of luck with all of these presentations.
Thank you.